Hello and welcome back to Coded Universe. If you joined us for our journey through linked lists, you're ready for the next step, learning about their operations. Last time, we unraveled the mysterious world of linked lists, their structure, and how they can be used to store and manage data. Today, we'll delve deeper into the operations that make linked lists so versatile: insertion, deletion, and traversal. So, ready to dive into the operations? Buckle up and let's get started. Imagine adding a new car to a toy train. In linked lists, insertion is just like that, adding a new element at a specific position. And the beauty of it? You can insert this new element wherever you want in the list, at the beginning, in the middle, or even at the end, just like you can add a new car anywhere in your toy train. So how do you do that? Let's say you have a linked list with 3 elements, A, B, and C, and you want to add a new element, D. If you want to add D at the beginning, you simply point D to A, and update the head of the list to D. Now your list starts with D, followed by A, B, and C. But what if you want to insert D between B and C? In that case, you first need to locate B. Once you've found B, you point D to C, and then update B's pointer to D. Voila! Your list now reads A, B, D, and C. What if you want to add D at the end? You just locate C, the current last element, and point it to DD, being the new last element, points to null, signifying the end of the list. See? Just like adding a new car to your toy train, you can easily insert a new element in your linked list. Deleting from a linked list? It's like removing a book from a shelf. The rest of the books adjust to fill the gap, keeping the sequence intact. Let's dive deeper into this concept. When you want to remove a book from your shelf, you simply pull it out, right? But what happens next is key. The books on either side don't just hang in midair. They shift to fill that space, maintaining the continuity of the row. The same thing happens in a linked list. When you remove or delete a node, the list doesn't break or leave an empty spot. The node preceding the deleted one simply adjusts its link to point to the node that followed the deleted one. In essence, it skips over the deleted node, bridging the gap and keeping the list intact. But what if you want to delete the first node? That's like pulling out the first book on your shelf. There's no book before it to adjust. Right, in a linked list, this is where the head pointer comes into play. The head pointer simply adjusts to point to the second node, effectively making it the new first node of the list. And what about deleting the last node? It's like removing the last book on your shelf. The penultimate book, or node in our case, simply adjusts its link to point to null, indicating the end of the list. Just removed a book from your shelf? Well, you just performed a deletion operation in a linked list. Traversal in a linked list is like hopping from stone to stone across a stream. You visit each stone or node to reach the other side, the end of the list. Now let's break that down. In the context of a linked list, traversal means visiting each node, one after the other, from the start to the end of the list. But why do we do this? The answer is simple. Traversal allows us to access each element in the list. Imagine if the stones across the stream were covered in moss. To clean them, you'd need to visit each stone, right? Similarly, traversal is necessary in linked lists when you want to perform an operation on every node. To traverse a linked list, you start at the head, the first stone in our stream, and follow the links from one node to the next until you reach the last node. This is akin to jumping from one stone to the other until you've crossed the stream. It's important to remember that, unlike an array, you can't directly access a node in a linked list. Hence, traversal is a fundamental operation for linked lists. It's your bridge to cross the stream, or in this case, to access the data stored in the list. You've just hopped over all the stones, or in linked list terms, you've just traversed your list. These operations are crucial in applications like playlist management, where you add, remove, and play songs in order. Imagine this. You're jamming to your favorite tunes and decide to add a new song to the mix. That's like inserting a new node into a linked list. Now, let's say you've had enough of one particular song, so you decide to remove it from your playlist. This is the equivalent of deleting a node from a linked list. And finally, when you hit play and let your playlist run from start to finish, you're essentially traversing the linked list. It's not just music playlists. Linked lists are everywhere. They're in your web browser's history, image viewers, and even in the undo functionality of your favorite text editor. So the next time you're managing your playlist or simply browsing the web, remember you're actually performing linked list operations. Next time you manage your playlist, remember you're actually performing linked list operations. You've now mastered the art of tinkering with linked lists. What a journey we've embarked on together, from exploring the basics of linked lists to understanding their operations. We've dabbled in the world of insertion, deletion, and traversal, and discovered how these operations are like adding a car to a toy train, removing a book from a shelf, and hopping from stone to stone across a stream. We've even seen how these operations play out in real-world applications like managing a music playlist. Remember, practice makes perfect. So go ahead and experiment with linked lists in your programming tasks. See how you can make your code more efficient and your programs more dynamic. I hope this video sparked a sense of curiosity and excitement about the world of programming. There's so much more to learn and explore. If you enjoyed this exploration, like, comment, and subscribe to Coded Universe for more programming adventures.